Hello students, welcome to lecture 5 in quantum mechanics. Now in the previous lectures we have been talking about the different postulates of quantum mechanics. Like we talked about that there exists a wave function in quantum mechanics, and we talked about the mathematical properties and the physical interpretation of the wave function. We talked about the operators in quantum mechanics. We also talked about the eigenvalue equation and the expectation value in quantum mechanics. Now today I will be talking about the last postulate in quantum mechanics, which is the Schrödinger equation. So the time evolution of this wave function, which we were speaking about so long in our previous lectures, the time evolution of this wave function for a given system goes in accordance with what we call the Schrödinger equation. Now what is the Schrödinger equation? How it looks like? The Schrödinger equation looks like this. I h cross del psi del t is equal to minus h cut square by 2m grad square psi rt plus v rt psi rt. So what are the different terms here? Of course you know that is I is the imaginary number, h cut is h by 2 pi, psi rt here is a wave function, m here is the mass of the particle in the system. This VRT is the potential energy. Okay, so here V is a function of R and T. So this is how the Schrödinger's equation looks like for a three-dimensional system. Okay, for a motion of a particle, for a three-dimensional motion of a particle. So this is Schrödinger's equation, and just like in classical mechanics, you had solved Newton's equation to know the entire information about the system. So here in quantum mechanics, now we will be solving this Schrödinger equation for a given system, and we will be finding out this psi rt by solving this equation, and this psi rt will give us all information about the system. So this is in 3 dimension. Now let us write down the same in 1 dimension. So if you write down in 1 dimension, this psi will then be a function of, say if the motion is along x direction, psi is a function of xt. So I h cut del psi del t equal to minus h cut square by 2m grad square psi xt plus, so sorry, this is del 2 psi del x square, since it's in 1 dimension, plus v xt psi xt. So this is how Schrödinger's equation looks like in a 1D system. So this is how it looks like. So now another thing you should know, that we are saying that if we solve this equation, we are getting psi xt. So if psi xt is a solution of this equation, now c, some constant c into psi xt will also be a solution of this equation. And how we find out this constant c? From the normalization condition. The normalization condition will be mod c square mod psi square dx will be equal to 1 from minus infinity to plus infinity. So once you know psi here, then you will also get to know, so you can find out c from there, from this equation, if the psi is given to you. So same thing here, if psi rt is a solution of this equation, then c psi rt is also a solution. And here you will be applying again the normalization condition, that you will be integrating over all space, and you will be having c square mod psi square dv to be equal to 1. So once you know psi, you can find out this c. So now we should know the technique of how to solve this Schrödinger equation, right? Because it's a second order differential equation, as you can see, but you can see that it is not that easy to solve, though it's a second order partial differential equation. But as you can see that on the left hand side, you have the dependence on time, and psi is a function of x and t here. On the right hand side, it is del 2 del x square. Here also psi depends on both the space coordinate and time. So there should be a definite technique that we need to know to solve this equation. So now I will talk to you about this technique. Now this form of the equation which you are seeing, whether in 1D or 3D, it is called the time dependent Schrodinger equation. It is called the time dependent Schrodinger equation. Now what we will do is, we will apply the method of separation of variables, and we will separate the time part and the space part of this equation, and then solve the time part and the space part and put the solution together. So let's see how we do it. So, and in this process we will be finding out the time independent Schrodinger equation from the time dependent one. So now what I am doing is finding out the time independent Schrodinger equation from the time dependent one. So let us take for 1D, it is easier to understand for 1D. So del psi del t, so the function of x and t is equal to minus h cut square by 2m del 2 psi del x square, where psi is a function of x and t, plus v into psi x. Now here this potential energy in this case, we will consider it to be a dependent only on the space coordinate. Okay, so we will consider it does not depend on time, because these are the cases mainly that you will be applying the Schrodinger equation to in the future classes. So we consider this v to be a function of x here only. Now I said that we will be applying the method of separation of variables. What I mean by that, I assume a solution that let psi xt be equal to some function of x only multiplied by some function of time only. So psi xt is equal to psi x, which is a function of x only, into phi t, which is a function of time only. Okay. Now what I will do, since I say that this is a solution of this equation, so therefore this should satisfy this equation. So what I do is, I find out del psi del t and del 2 psi del x square and substitute it back in this equation. So del psi del t, obviously since this psi here depends only on x, so when I am taking the differentiation with respect to time, so only this part will contribute. Now psi here is a function of both x and t. So when I take the time derivative, I take the partial derivative, but this phi is solely dependent on t, so I can write it as a total derivative d phi dt. So del psi del t I have found out. Next I have to find out this del 2 psi del x square. So first I find out del psi del x. So del psi del x, so now this psi is dependent on x, but this is dependent only on t. So this will not contribute, but this psi will contribute. So it will be d psi dx. Okay. So again this is dependent only on x, so I can write this as a total derivative. Now if I do the differentiation another time, del 2 psi del x square, then also this phi t will not contribute, and this result will be phi t into d2 psi dx square. Okay. Now we will put this expression of del psi del t, del 2 psi del x square and psi xt in this equation. So let's do that. So I h cut, this is psi x into d phi dt minus h cut square by 2m. This will be phi t into d2 psi dx square plus v, a function of x, and here I have psi as a function of x and phi as a function of time. So I just put it here. Now we can easily separate the time part and the space part by just, I think you can also realize from this equation which I have written, that if you divide this whole equation by the product of this psi and this phi function, then the time part and the space part will be separated. So let's do it and see what result we get. So I have divided it by psi into phi. So psi cancels and I have this here by 2m, and this will be 1 by xi d2 xi dx square plus vx. Okay, so here this xi is a function of x only. So now you can see that the left hand side here is dependent only on time and the right hand side is dependent only on this x coordinate. Okay, now since both are equal, then I can say that both these side, left hand side and right hand side, is separately equal to some constant. Okay, so I write down the two equations separately. So from here I get two equations separately, since the left hand side is a function of time and the right hand side is a function of x only, but they are both equal, and this is only possible when individually both the functions are equal to some constant. So therefore I can write that this is equal to some constant, is equal to the same, and both of them are equal to the same constant, so that constant I name it as E, and the right hand side I can write it as this right hand side equation. This is also equal to E, where E is a constant. So now this equation solely depends on time, this equation solely depends on x. So if I just rewrite this second equation, then it looks like this: minus h cut square by 2m d2 xi dx square plus vx into xi x is equal to some constant E into xi x. Okay, so this equation, it is independent of time, and this is what we call the time independent Schrodinger equation, and we will be using this equation in our future applications to different systems to find out this function xi x from here. So this is called the time independent Schrodinger equation. So, and there is another way of representing this equation. So you can just see from here that this minus h cut square by 2m d2 dx square plus vx, this whole thing represents an operator which I have discussed in earlier class. This whole thing represents an operator which I have discussed in earlier class. I don't know how many of you are able to identify it, but you should be able to do it. So this is the Hamiltonian operator. So I can also write this equation as h cap, because this entire thing is the Hamiltonian operator, h cap xi x equal to some constant E xi x. So this is another way of representing the time independent Schrodinger equation, and you can well understand from here that the h cap operator operating on xi x gives me back xi x into some constant. So definitely the xi x is the eigenfunction here, and this E is the eigenvalues of this operator h cap, and we know that here the v is only a function of x, so h cap definitely here is the energy operator. So this E is the result of this energy operator. So this E has a physical significance. It is called the energy eigenvalues, and that is why we have named this constant purposely as E to denote that this is the energy eigenvalue. Okay. So this is a time independent Schrodinger equation. Now what about this part? This part depends on time. So if I solve this equation, I should be able to find out this phi as a function of time. So let us find out this phi as a function of time, because after all we have to solve the equation, right, and get the solution of xi xt. Remember, we started with the time dependent Schrodinger equation, and our aim is to solve xi xt. Okay. So to solve xi xt, and if you remember, we have written this xi xt as xi x into phi t. So this I know I have to solve the time independent Schrodinger equation to get this. So to get this, I have to solve this equation. It's very simple. So what I get from here, let's work this out quickly. So I can rewrite this equation as d phi by phi equal to E by I h cut dt. right? So if I integrate this, then it is log phi equal to E by I h cut t plus some constant, say log c. If I multiply this by I and divide it, so it will be minus IE by h cut t plus log c. So this can be written as log e to the power of minus IET by h cut plus log c. So therefore the function phi t, as you can see from here, can be written as c, some constant c into e to the power minus IET by h cut. Right? So this is how the function phi t will look like, where E is the same energy eigenvalue that we were talking about. So now we know how phi t looks like. So if I just put in this equation, so let us see how this psi xt will look like. So psi xt will be equal to this psi x into some constant. You can put the constant equal to 1 also if you wish to, or you may keep it. So into e to the power of minus IET by h cut. So this is how this psi xt will look like. So to solve Schrodinger's equation for a given system, from now on what we will do, we will write down the time independent Schrodinger equation for that system, and all the, for a given system, definitely the potential energy we will be knowing and the boundary conditions we will be knowing, and from there we can find out this psi x easily, and we'll put this psi x in this solution, and this part will always look like this minus IET by h cut. And definitely if we will know this psi x, we will be also able to find out this energy eigenvalues. So this will give us, putting this psi x here and this energy eigenvalues will give us the complete solution of this equation. Now just note one interesting thing from here. If I take the conjugate of this function, then what I have? If we just say the conjugate, so of course the imaginary part will change sign, and if you multiply this psi into psi star, you will get mod psi x square. And what does psi star represent? It is the probability density. So the probability density, you can see for a Schrodinger's equation, it is always independent of time. So this means that the states of the different states in quantum mechanics, they are stationary states, because the probability density will always be independent of time. Whenever I will multiply this solution with this conjugate, the time part will vanish because of this imaginary term, and I will get it to be independent of time. So in the next class, I will teach you the application of this Schrodinger equation. Thank you.